All right, welcome. In this video, I'm going to talk to you about reparametrization with respect to arc length. What it is, how you do it, and why we're not going to do it all that often in this class. Okay, so first I need to start with the idea of the arc length of a parametrized curve, which we have already talked about. Okay, so if S is the length of vector valued function r of t on the time interval a to b, then S is the integral from a to b of the square root of x prime squared plus y prime squared plus maybe z prime squared if we're working with a space curve. If we were working with a plane curve, we'd just ignore that z prime, just x prime squared plus y prime squared there. Okay, but what I want to do is I kind of want to think about the arc length, the distance traveled as a function of time, like small s of t being how far have I gone along the curve as time has gone on past the beginning point t equals a. So we're going to define the function s of t to be the integral from a to t of that same square root. Okay, so t is now just going to be how far are we integrating this same thing. Okay, now I'm going to point out that s prime of t, that's the type of thing that we could use the second fundamental theorem of calculus for, that the derivative of a function defined by an integral is we would plug in that t wherever we saw the dummy variable in the integrand, so we'd have, just that square root. Okay, but then I also want you to notice that that square root, that's the length of r prime of t. And that we could also call s prime of t ds dt, okay, because that's something that you're going to be seeing, especially if you're interested in where the formulas for curvature come from. Okay, so we've got ds dt is the length of r prime of t. Also, I would point out that as a result from that, we could say that ds is equal to the length of r prime dt, and that's mostly relevant if you're thinking about that formula for the area of surface of revolution that we talked about, kind of a little bit earlier. Okay, so from all of this discussion, what we really are going to need is the formula for s, and then these couple of ideas or expressions for the derivative of s. That's what we're going to need. Now, to show you how this is going to work, I think it's going to be best for me to just go ahead and do an example. So here we've got f of t, which is 2t plus 1, 3t minus 1, and 6t for t being greater than or equal to 0. And I'm going to say reparametrize f with respect to arc length. Okay, so what we're going to do is we're going to calculate the arc length of this thing. And notice that this is the graph of this function is not very interesting. It's a line. And that's going to get to my kind of bigger point at the end about the utility of this. But we're going to start by, just computing s. So we need the formula. S of t is the integral from a to t of the square root of x prime of v squared plus y prime of v squared plus z prime of v squared, all with respect to u. Okay, so for us, a is going to equal 0 because this is kind of the starting value of my time interval. Okay. Also, I'm going to need f prime of t. I take the derivative of f, and I'm going to get 2, 3, 6 at every t. And that'll be nice because then when I go to, plug that into the formula, I'll be taking the square root of 2 squared plus 3 squared plus 6 squared with respect to u. Okay, and you add all that up and you see, oh, that's the square root of 49. Okay, so this is a good sign. Okay, I know how to take the square root of 49. That's 7. Okay, and then an antiderivative for 7 with respect to u, that's going to be 7u. And we're going to let u run from 0 up to t. And we're going to get 7t minus 0. And so that's telling me that s is equal to 7t. And if s is equal to 7t, then that means that t is equal to s divided by 7. And now what I'm going to do, I'm going to just plug in s divided by 7 wherever I see t in the formula for f. And this is what we would call reparametrized with respect to arc length. So if I plug in s equals 1, that's going to give me the point on the graph of f where I have traveled 1 unit away from wherever I was at t equals 0. If I plug in s equals 100, that's good for, where I'll be at after I've traveled 100 units of distance. And I think it's pretty self-evident that that would be a pretty useful parametrization of a curve. It's just that that's kind of sometimes hard to come by. Whereas a time parametrization is oftentimes much more natural. Okay, so that's kind of leading us to the other question I can kind of ask you that goes to reparametrization with respect to arc length, and that would be something like, okay, what's the position of the object traveling along the curve defined by f of t after it's traveled 14 units? And I'll say, all right, well, I'm just going to use f of s where s is equal to 14. And so I'm going to plug into f, and I'm going to get 4 plus 1, and 6 minus 1, and 12, which is going to be 5 and 5 and 12. All right, let's do another one. So here we've got g of t, which is 2 cosine of 2t, 2 sine of 2t, and 3t for t being greater than or equal to 0. And the graph of this thing is going to be a helix. And so we're going to reparametrize g with respect to arc length. So we'll start off with, we'll need the formula for s. And then we'll need x prime, y prime, and z prime, so we're going to need to take the derivative of g, and I'll do that off to the side. And I'll get negative 4 sine of 2t, 4 cosine of 2t, and 3. You need to be careful about the chain rule there. And then we'll set up our integral, and I'll have the integral from 0 to t of 16 sine squared of 2u plus 16 cosine squared of 2u plus 9. And I'm going to factor out the 16 from that sine squared plus cosine squared because I got the same argument. I'm going to use that trig identity. And you'll see, okay, that's going to be 16 times 1 plus 9. That's going to be the square root of 25. And this is something I know how to anti-differentiate, right? Antiderivative of 5 with respect to u is going to be 5u. And I'm going to let u run from 0 up to t. Then when I plug that in, I'll get 5t. Now I've got s equals 5t. Okay, and as a result, I can conclude that t is going to be s divided by 5. And then from there, I'm just going to go back to the formula for g of t. And yeah, if I want g of s, I'm going to replace t with the formula for s wherever I see it. And I'm going to say, all right, g of s is going to be 2 cosine of 2s over 5, 2 sine of 2s over 5, and then 3s divided by 5. So if I'm asked, what's the position after traveling 5 pi over 3 units, I'm going to use s equals 5 pi over 3. I'm going to plug in on g of s. So if I let s equal 5 pi over 3, that means g is going to be 2 cosine of 2 pi over 3, 2 sine of 2 pi over 3, and 1 pi. Okay, now it might have been a while for you since you've gone and looked up cosine of 2 pi over 3, but I'm just going to remind you how we can do that. We can just draw ourselves a little triangle. Go to theta equals 2 pi over 3, you know where that is. Draw yourself a little 30, 60, 90 reference triangle, and do SOHCAHTOA, right? It's been long enough, we don't really need to have the thing memorized for multivariable calculus. We just need to be able to occasionally draw a triangle and use it, right? Alright, so for 2 pi over 3, cosine is going to be adjacent over hypotenuse is negative half. Multiply that by 2, I get negative 1. 2 sine is going to be positive square root of 3, and then pi is not really depending on that trig diagram. So I'm going to have negative 1 square root of 3 and pi. That's great, but let's take a step back for a second. Let's think about how this all went down, and also the other example. So really, the only reason we were able to compute that integral was because we were able to apply that trig identity right there, and that we ended up with the integral from 0 to t of a constant. And so really, this reparametrization with respect to arc length is only working well when the derivative has a constant length. Otherwise, it's really unlikely. I mean, you took AP Calculus probably, and you remember those arc length integrals. They were really unlikely to be able to be computed by hand. And if we look back at the case of the parametrized line, it's the same thing. It's like, oh man, because the derivative had a constant length, we were able to compute this. But if it wasn't, then s would be, kind of like an unresolved integral. And that's definitely not something you really want as your independent variable. In your parametrization as an unresolved integral. So in practice, this is not going to be all that easy to do or compute or work with. But the idea of reparametrization with respect to arc length will be important for, when we go to develop the curvature formulas. And I'm going to use kind of this idea and I think some of the formulas in that video. But definitely reparametrization with respect to arc length, something I mentioned in my multivariable calculus class, but not something we're going to need to be able to do, or something you're going to have to do on a quiz or a test or anything like that. So that's going to be all for this video. Thanks for watching.